bridges.
Too much drip, I'm a shower. Can't see the top, all my money is the tire. Ready pop shit, but my candy always sour. Touch it like flowers, well, bitch, I like flower.
Y'all know the drill. In my second year of engineering, we received the challenge to make a scale cable stayed bridge, with emphasis on material efficiency, structural efficiency, and aesthetic. A cable stayed bridge has one or more towers from which the cables support the bridge deck. If we load this bridge, this load will be transferred to the cables. These cables then transfer the load further to the pylons, which then transfer the load further to the foundation. Of course, there were some rules. The bridge had to be entirely made out of a MDF plate, which stands for medium density fiberboard. In terms of dimensions, the bridge had to be 2.40 meters long with a span of 2 meters, a width of 0.40 meters, and a depth of 6 millimeters. Most importantly, the bridge had to be able to withstand 100 kilograms with a safety factor of 2, meaning it should be able to hold 200 kilograms, but it should fail if we add more weight. In terms of deflection, only a 2 centimeter deflection was allowed. Last but not least, it had to be unique. With this in mind, as with every other project, we started brainstorming ideas for the design of the bridge. We wanted this bridge to be unique as possible and an absolute eye-catcher, so we came up with this original design inspired from the Erasmus Bridge in Rotterdam. Our supervisors warned us the calculations for this design and building it would be an absolute pain in the ass. And they're right. Because of the non-symmetric design, there's one pylon that introduces a huge momentum because we're actually pulling on the weak side. Since we're working with a lot of angles in the design, we had to keep in mind to make the pylon strong enough to withstand the buckling. There were a lot of other small details, but I would say these were the two main ones. Anyway, we ignored our supervisors and put our engineering brains to work. We started off by carrying out a lot of tensile tests on the MDF material, cables, ropes, etc. Each test would give us a graph from which we could determine the elastic modulus from. This was important because we need these values to fill in SIA, a structural analysis software, so it knows what material we're using and we can then run some simulations on the bridge so we could see how it would respond to the load. We wrote some code in Python allowing us to calculate the force working in each node and cable, so we had a clear idea what material would be strong enough to use for the bridge. Using 100% of our brain capacity, we then verified these calculations on paper and made a decision what material we would use for the bridge. Oh yeah, this took us 4 days, by the way. We then spent the remaining 2 days building the bridge and putting it to the test. Here's a little time lapse. As you can see, we cut out the shape of the pylons and then glued them together so it would increase the strength. We also cut out some metal parts for day 2. We then spent the remaining time preparing the bridge deck. On day 2, we then added the pylons to the bridge as well as the ropes and the cables. We then finished the bridge by painting it white to give it a modern look. It was now time to test the bridge and put on the weights. can see, it was able to hold 100 kilograms with a safety factor of 2. However, we did have a deflection of 4 centimeters instead of 2, but it worked out. Thanks for watching.
Too much drip, I'm a shower. Can't see the top, all my money is a tire. Ready pop shit, but my candy always sour. Said she like flowers, well, bitch, I like flour.